All right, welcome to part 3 of solving mazes with reinforcement learning. So part 3 here, we're going to actually start creating some of our models. We're not going to do the Intrinsic Curiosity module yet, but we are going to do the actor and critic models. So here we're going to create a model.py, and we're going to import some of our core libraries. So torch, import torch.nn as nn, import torch.nn.functional as f, from torch.distributions, import normal, import os. We're going to declare a few constants that we'll need later, log sig max, and log sig min, and epsilon equals 1e minus 6. Don't get this confused with epsilon that you would see in like epsilon greedy actions with Q-learning. This is the same variable name, but it's not used in the same way at all. We're going to declare a function to initialize policy weights, and that's going to be weights init m. And you don't have to do this, but starting with, we're going to be using Xavier initialization, and that's going to start us with a more standard spot for the models each time. You could skip this step. Models would just initialize, randomly. So in this scenario, we're going for something a little bit more stable. So we're saying if is instance m nn.linear. So basically, if you're passing in a linear layer, then torch.nn.init.xavier uniform, m.weight, gain equals 1, and then torch.nn.init.constant m.bias 0. And there's nothing super special about this. You could use other initialization methods. This is the one I happen to use here. All right, so we're going to start out, we're going to move on to our Q network. This is our critic, our value network. So we're going to call it, shocker, Q network. Actually, let's call it critic. And then .module. And we're going to say, we're going to set up our init method. And this is going to have quite a few things. Self, num inputs, num actions, hidden dim. I'm going to pass in a checkpoint directory, and we'll default it to checkpoints. And we're going to give it a name. Will be Critic Network. All right. And here we're going to call our super method as usual with critic and self, and we'll call init. And then we will actually start declaring our layers. So if you recall from our draw IO, our critic is going to have an input layer that will be state and action. It'll have a couple of linear layers, and then it'll have an output layer. So we're going to, and we're actually going to be using a dual critic. That's something I haven't really talked about yet. So we use a dual critic to stabilize learning. With one critic, you can end up with it bouncing around a little bit in its evaluations. With a dual critic, we're going to take the lower value, so we'll compare the two and take whichever one is a lower value, and then we will run an update on the second critic every so often, and that actually helps stabilize learning a little bit. So with that, let's go ahead and we'll say critic 1 architecture self.linear1 equals nn.linear, and this is going to be num inputs plus num actions. Remember, we're taking both, and hidden dim, and we're just going to copy that to the next line and call it self-linear2, and except this will be hidden dim, so it's got the same value on input and output. And then we're going to say copy it to self.linear3, except in this case it's going to have one output. All right, and then we can just copy all of this down here, and we're going to change this to critic 2, and these will be linear 4, 5, and 6, and otherwise nothing changes. We're going to set, here I'm going to pull up some of that space there. We're going to set a few variables that we'll need later on. So self.name equals name, self.checkpoint_dir equals checkpoint_dir, and self.checkpointFile equals os.path.join self.checkpoint_dir name plus, we're going to do SAC to name it. And then finally, we're going to apply those weights up here that we set up earlier. So we're going to say self.apply weights init. All right. So what are we doing here with checkpoints? So from a design perspective, one of the things I like to do is I don't want to have to externally, I always want to save my models. That's what the checkpoints are. So as it learns every so many steps, it's going to go ahead and save a copy of the model off. Some people are going to, say if you get a new high score, save a model. I'd rather just do one every so often because I like to see how it's doing as it trains. And then I like to build that functionality into the networks themselves so that we can just call the network and tell it to load its models and have it be smart enough to do that without having to necessarily have that logic external to the model itself. So, all right, here we're going to say, we're going to go ahead and define our forward method. So the forward method, if you haven't seen this before, is basically the thing that gets called by default if you just call the model, pass in an input, and expect an output. The forward method is what's getting called. So in this case, the critic is taking the state and action taken, and taking some actions against it. So, or not taking action, it's critiquing, deciding what the value should be. So we're going to say xu equals torch.cat, more concatenation, state action 1. So we're just like we did in the environment, concatenating the observations. Here we're concatenating state and action into one layer, and then we're saying x1 equals f.relu self.linear1. So we're basically saying we're applying the first and second linear layers here. So we'll say linear 2, and then down here we will not be applying our non-linearity. We will just be saying self.linear 3 x1. All right, and then just like before, we're going to copy all this except x2, and this will be linear 3, 4, and 5, except I messed that up. That's linear 3, so this is linear 4, 5, and 6. All right, so we could have also done this as 2 separate networks. The way we're doing it, though, is we're effectively getting 2 different responses from 2 different sets of layers and weights from the same model, and it works pretty well. And then we're returning x1, x2. All right, and then we just need to write some of our, sort of base save and load functions here. So we're going to do a save checkpoint. Gotta include the boilerplate stuff. And we'll say torch.save, self.stateDict, and we're saving to self.checkpoint file. And again, this is the cool thing about this solution is that we are, all of this is self-contained, so you can always call, save checkpoint, or we're about to define a load checkpoint, and it will know, it'll have the appropriate state dictionary because it's itself, and it will always have the right checkpoint file. So we're going to say def load checkpoint self.load state dict torch.load self.checkpoint file. All right. So let's go ahead and we're going to test this model and end the video after that, and we'll pick up doing the actor model in the next video. So let's go ahead and just go make sure that this works. For now, I'm going to comment out some of the END stuff, and we're just going to say from model import star, and we'll say model equals model, let's see, here, we'll do critic equals critic, and we'll just pick some random values. 1, 1, we'll do 1, hidden dim, and then we'll leave everything else the same. Critic has no attribute linear 1. So this is why you want to test things as you go. You don't want to find out later that things are broken. And I see what I did. I think I did some very, very stupid syntax error there. I did a double equals for all of these, which is an equivalency check. It is not an assignment check, and that will definitely cause problems. Okay, observation's not defined because of course it isn't. I didn't get it because I commented that out. And we have a successful call of the critic. All right, so we have a critic model. Obviously we haven't fully tested it, but if you followed up to this point, you should at least be able to run it and get no syntax issues. And we will go ahead and set up the actor model in the next video.